Hello and welcome to this next lecture on Python power electronics. I want to talk about the basic concept of magnetism. Here is a diagram of a simple magnet as we all know. This is a simple cylindrical magnet with a north pole and south pole. This is the link from Wikipedia which they need us to acknowledge if you use their content. You can use this link if you want more details. You see that there is a north pole and a south pole. This is the case with almost any magnet. The poles always appear in pairs. You cannot just have one magnetic pole. This is the case also in electrical engineering. The magnetic lines of force originate at the north pole and terminate at the south pole. If you look at these curved lines, these are the magnetic lines of force. And the arrows indicate the direction of the magnetic field which start at the north pole and end at the south pole. In electrical engineering, the magnetic lines of force always start at a north pole and end at a south pole. The reason for this difference is that sometimes, particularly in electrical machines, you may have several north poles and several south poles. You have several pair of poles instead of a single magnet. Magnets have a wide range of uses. We will talk only about the case in power electronics. The reason I want to describe this is because I felt the need to introduce some concepts of magnetism since a lot of power electronics is heavily influenced by magnetic fields and stored energy, if not deliberately then accidentally. In any electrical circuit you will have a magnetic field. Take any conductor carrying a current. The current will produce a magnetic field. You see the circles of red lines, and these are the lines of magnetic force. Here, there is a difference from a magnetic dipole shown before. However, the magnetic lines of force still have a direction, and that is always the case. The way to determine the direction of the magnetic lines of force is if you hold the conductor with your right hand and only your right one, and in such a way that the thumb points in the direction of the current. In this case, the direction of the current is upward and the thumb is pointing in the direction of the current. The direction in which your fingers encircle the wire as you hold the wire is the direction of the magnetic field. And if you see, that is exactly the case. The hand holds the wire and you'll see that the magnetic lines of force are exactly in the same direction as the direction in which the fingers are encircling the wire. This image is from Wikipedia, and so this is the link if you want more details. This rule is called the right-hand thumb rule. This is the impact of magnetic fields in electrical circuits. In any circuit, there are numerous wires with current flowing through them. This implies, any electrical circuit is producing a vast multitude of magnetic fields surrounding these wires. And this is the reason for this introduction to magnetism, as soon we will use this to discuss the concept of an inductor. And going further, that is the basis of almost every electrical machine where energy is converted through a magnetic field. The strength of the magnetic field is called the flux density. This flux density is basically the number of magnetic lines of force that pass through a square meter area. The unit of flux is Weber, and therefore that of flux density is Weber per square meters. The flux density depends on the magnitude of current passing through the conductor. The flux density also depends upon the nature of the medium through which it passes. In the case of the previous example, the lines of force were passing through air, in which case the medium was air. Air is not a medium that allows flux to pass through it freely. This property of the medium that allows or doesn't allow magnetic field to pass through is called permeability. The permeability depends upon the medium. Some media allow magnetic fields to pass through to a much greater extent, resulting in higher values to flux density, and these are said to have greater permeability. And there's some media which will not do so. For example, air has very low permeability, and so the magnetic field that is produced by just a wire like this passing through the air is going to be very low. It's not just the permeability that matters. It is also the magnitude of current. If it's just one single conductor surrounded by air, the magnetic field will be negligible. And this is why you don't feel it even though you're in a house with wires all around, because there's not much magnetic field produced. Of course, this will change if instead of looking at just a normal wire at home, you look at a high voltage line with thousands of amperes of current. Now the magnetic field is significant. This is one of the reasons why there is a safe distance maintained near a high voltage line, and it is advised not to live or pass near a high voltage line, as those magnetic lines of force can have an effect on the human body. This was a very basic introduction to magnetic fields in electrical engineering. You are welcome to read more on magnetic fields if you are interested. But this is just an introductory lecture before I describe the concept of inductors and energy stored in magnetic fields produced by inductors that are used heavily in power electronics. If you have any doubts, feel free to post in the Q&A, or otherwise I will see you in the next lecture. Thank you so much and goodbye for now.